morning, everybody. Today we're going to do experiment number 3, quantitative analysis of iron 2 plus iron, Fe2 plus iron, in an N-known iron sulfate sample. And matter of fact, it's an iron ammonium sulfate in the sample that we're using. Okay? And the primary objective of today's experiment is we want to determine the percentage of iron in the sample of iron ammonium sulfate with impurity. Now again, if we know the formula, if the sample is pure, there is no need to perform all this experiment. We can, based on the formula, we can determine the percentage there. But the unfortunate thing here is that more than often when you work in the laboratory and the sample comes in, the sample is impure. So if the sample is impure and there's only one thing that we're interested in that sample to quantify, well, we have to go through these processes here. Now this particular experiment requires a chemical reaction that we call redox reaction. And when you finish Chem 101, we talked about redox reaction in Chem 101. When you finish Chem 101, you remember redox reaction, oil rig. Oxidation is the loss of electron, and reduction is the gain of electron. Okay? So in terms of the terminology, we want to review the redox reaction, and then we're going to be using the process of titration to determine how much iron is present in a given sample. Now, to do this experiment, we actually have to perform two different activities. The first is that we need to determine the molar concentration of potassium permanganate solution. Potassium permanganate is a strong oxidizing reagent. Now, we need to determine the concentration using a sample with a known percentage. And then, once you know the molar concentration of the solution, potassium permanganate solution, then we're going to give you an N-known sample, and you repeat the process again doing the titration. From there, you can determine the percentage of iron in the given sample. Okay? So safety is always our top priority when we work in the lab there. Wear your goggles, wear your gloves, and make sure you follow the instructions for waste disposal. Don't pour anything down the sink. We always have a waste container in the laboratory where you can dispose of all the unwanted chemical waste. Okay. So in terms of the reaction, and going back to the redox reaction, you may remember in Chem 101 we're talking about, for redox reaction there, we're talking about one part electron is being received, the other part electron is being given out. So let's write out the chemical reaction equation, the ionic chemical reaction equation, in something that we call the half reaction. For the half reaction of the reduction, now remember reduction is the gaining of electron, well this is what's happening here. This particular experiment has to happen under acidic condition. So in acidic condition, we need to use hydrogen ion or hydronium ion when we try to write out the balanced chemical reaction equation. Potassium permanganate, KMnO4, we're using the net ionic equation. These two will interact with one another, and along with the 5 electrons provided by someone else. We're going to be looking at who's going to give out the electrons. So this is the reduction side of the reaction. Electrons are being received. So in this case, what we want you to pay attention to is that the manganese in this particular formula, manganese has a positive 7 oxidation number. When everything is said and done after the reduction, Mn becomes 2 positive, becomes a species with 2 positive charge. So 2 positive charge, the oxidation number is +2. So going from positive 7 to positive 2, how do you do that? You have to gain 5 electrons. So we put 5 electrons on the left side of the equation. This is the half reaction for the reduction. Now, for the half reaction of the oxidation, we have Fe2 plus in the given sample. Okay? Fe2 plus is being oxidized into Fe3 plus. So in this case, each Fe2 plus is only giving out 1 electron. Well, if you look at the first half reaction, we need 5 electrons. This process only gives you 1 electron. We need 5 electrons. How do we get 5 electrons? Well, we multiply everything by 5. So overall, the 5 Fe2 plus will be oxidized into 5 Fe3 plus, with 5 electrons being released. And with the 5 electrons being released, those 5 electrons will be picked up by the other side of the reaction. If you put these two half reactions together, this is the overall redox reaction. Okay? Under the acidic condition, we have potassium permanganate with 5 moles of Fe2 plus. We end up with Mn2 plus, and we end up with water. We end up with 5 Fe3 plus. So this is the overall reaction. What's important here is that when you look at the overall reaction, there is a molar ratio, there's a relationship between the number of moles of KMnO4 and number of moles of Fe2 plus. Okay? So this 1 to 5 molar ratio is the basis for us to do the calculation. So as we said, for doing this experiment, first we need to determine the molarity of the KMnO4 solution, potassium permanganate solution. So this is the calculation involved on how we determine the molarity. We are going to give you a sample with a known iron percentage. So if you measure out 1 gram, half gram of that sample, we can determine the mass of the Fe2 plus alone in that given sample. And that can be done by using the percentage number that is given to you and multiply by the mass of the sample. If you have 1 gram, half gram of the sample, and then we tell you the percentage of iron in that sample is, say, 5%, 6%. Well, using that 5%, 6%, multiply by the mass of the sample, that will give you the mass of the Fe2 plus in the sample. Now, if you know the mass, you can convert it into moles. We know that each mole of Fe2 plus is equivalent to 55.85 grams. Okay? So if you get the mass from equation A, multiply that by the conversion factor, 1 mole equivalent to 55.85 grams, you get the number of moles of Fe. Now, once you get the number of moles of the Fe2 plus, you can convert it into the number of moles of KMnO4. So the number of moles of Fe2 plus multiplied by 1 over 5. This conversion factor came from the balanced chemical reaction equation where you have that 1 to 5 molar ratio. Okay? And then once you get the number of moles, when you do titration, you will also be able to figure out the volume of the KMnO4 solution. So the number of moles divided by the volume will give you the molarity. So that's the first part of this experiment. Okay? And then the second part of the experiment there, we're going to give you an N-known sample. When you have an N-known sample, this is already known, and this can be determined through the experiment. We can figure out C. Okay? So when you do calculation for the N-known part of the experiment, you go from D to A. When you try to determine the molar concentration of KMnO4, you go from A through D. Okay? The sample calculation given to you on page 4 of the lab manual is for figuring out the percentage. So here, going from A through D, we are trying to determine the molarity. And going from D through A, we can determine the percentage. So these two processes are opposite of one another. And once you have the percentage of the Fe2 plus in your N-known sample, we also want you to calculate the percent error. And again, the same equation, true minus the experimental divided by true times 100. And where to get the true value? The lab instructor will give you the true value, so you can calculate the percent error for your experimental result. All right, so for the experiment part, and this is how we do the experiment. Through titration, we know when you do titration, you need to use a burette. Okay? So I fill up the burette with KMnO4 solution. This is the prepared KMnO4 solution. The concentration is already given, but this is something approximate. We want you to determine the accurate concentration by doing the titration. So here we give you a sample of the iron ammonium sulfate with the given percentage. So this one's at 6.95%. Okay? So we measure out half gram of the sample. The lab manual requires you to measure out 3 portions of the same sample, okay, about half gram each, and record the mass accurately. Okay? Once you have the sample there, we want you to dissolve the sample in approximately 25 milliliters of 1 molar sulfuric acid. Okay? So we have the 1 molar sulfuric acid solution, and then just to acidify, improving the solubility and acidify the solution further, we want you to put 4 to 5 drops of phosphoric acid into the solution. So now I have all the samples dissolved with the with the acidic solution there, we're ready to do the titration. Now, just a quick review for the titration part. Once you fill up the burette on top says 0. On bottom, for this particular burette, it says 25 milliliters. So you can have as much as 25 milliliter of solution in here. But how much the burette holds isn't really something we care about. What we're trying to figure out is how much we are adding from the burette into the reaction mixture. And one thing that we do want you to pay attention to is that when you fill up the burette, the tip of the burette is filled with air. So you need to make sure that the tip is filled with the solution. So the first thing that we need to do really is to release some of the solution into a waste container, a beaker, okay? And then make sure all the air bubbles are driven out. Okay? So now you can see the tip of the burette is filled with the purple solution. Now when you do titration, sometimes you ask, well, don't we need an indicator to tell us when the reaction is over? Well, in this case, we're lucky we don't need the indicator because KMnO4 has a dark purple color. Okay? Once the manganese is being reduced into Mn2+, the solution has no color. So what we're trying to do here is that you have some Fe2+. As long as you have Fe2+ in here, the moment you put the potassium permanganate solution in here, you may see a brief presence of a pinkish solution. But if you swirl the flask, that pinkish color will disappear. You keep adding more KMnO4 into the solution, and then the pinkish color will disappear. The disappearance of the pinkish color will get slower and slower. And that's the time you need more patience. And you want to get to the end point where you have a very faint pink color present in here. And when you see that pinkish color, persistent pinkish color, that means there's no more Fe2+ in the solution. And when you see the pink color there, we know that we reached the end point. As always, when we do titration, I try to emphasize here, the point for titration is not for the color change. Rather, what is the minimum amount of chemical that is needed in order to reach that color change? If you dump too much chemical in there, you get the color change, but that doesn't give you any useful quantitative information. Okay, so let's do this titration together. We have a clear solution, everything dissolved in there. We're going to add potassium permanganate solution into the mixture there. And to visualize the color change a little bit better, we always recommend that you put a piece of white paper underneath the flask. Looking against a white background makes it easier for us to see the pinkish color. Okay? So when you do the titration there, and you open the stop cork and start swirling the mixture there, and you can see the persistence of the pinkish color. But if I stop adding the solution, and I keep swirling it, and you see that pinkish color disappear. Okay? So now it's clear. Okay? So that means we don't have enough KMnO4 yet. We just keep adding KMnO4. And you can see the disappearance of the pinkish color is getting slower. And once again, as I said, that's the time you really need more patience, not less. Okay? Sometimes you may need to add the titrant one drop at a time. What are we trying to get is that once you put that last drop in, you have a persistent pinkish color throughout the flask. And that tells you you have reached the end point of the titration. There we go. After that last drop added in there, you can now see there's a very light pinkish color in the flask here. That indicates there is no more Fe2+. Everything is being converted into Fe3+. So this is the end of the reaction. Okay? Now sometimes when you have a pinkish color, it may not persist for long. So we need to make sure that we swirl the flask for at least 30 seconds. If the color disappears within 30 seconds, you're not quite there yet. You just need to keep on adding more KMnO4 until you have a persistent pinkish color. So that's roughly about 30 seconds now, and you can still see that pinkish color, and we are at the end point. Now remember, you started at 0 from the Biuret reading. Now we have somewhere around 8.50 milliliter. So how much did we add into the flask? Well, 8.50 minus 0. We added 8.5 milliliter of the KMnO4 into the solution. Now we need you to repeat this process with the 6.95% iron sample. We need to repeat that 2 more times. Okay? And then going through A to D to try to figure out the molar concentration. And then we have N-known sample. Now you can see the N-known sample with a number there. It's N-known 7, number 7. We want you to use this sample, measure out 3 portions of this sample, repeat the process 3 more times so that you can determine the percentage of iron in this particular sample. So in a nutshell, this particular experiment, 6 titrations. 3 for the known part, trying to determine the molar concentration of the KMnO4. 3 for the unknown part, when you're trying to determine the percent of iron in the given sample. And again, the true value, you will need to ask your lab instructor, based on the unknown number of your choice, ask your lab instructor what is the true value. Once you have the true value, you got your experimental value, you calculate the percent error. And that is everything that we need to do in this laboratory. And again, waste disposal is very important. We have a container for waste disposal. Anything that you finish using, anything you don't need, you can dump it into the waste container.